Considering the function f of x equal x squared plus 5x plus 6 over x minus 3, we want to look at where this function is positive and where it's negative. Now, the critical points are the points at which the function can change sign. And we've seen that already. And for any rational function, for any function with a numerator and a denominator, any point where the numerator is 0 is a point where the function might possibly change sign, and any point where the denominator is 0 is a point where the function might possibly change sign. There's no guarantee that at any of those points the function changes sign, although that can be reasoned out in a reasonably straightforward way. However, that's the bottom line. You have critical points, and those points include all the zeros of the numerator and of the denominator. So what are the zeros of the numerator and denominator? Also, I've written a note here. The critical points, again, are the points at which the sign could possibly change. I wrote can change here. If I'd had more room and thought of it, I might have written the points at which the sign could possibly change. Well, in any case, it's easy to see what the zeros of the numerator are because the numerator is really easy to factor. It's x plus 2 times x plus 3, and we know that x plus 2 is 0 if x is negative 2, x plus 3 is 0 if x equals negative 3. Now, if that's something I can't factor, if I don't want to bother trying to factor it, I can plug that expression into the quadratic formula and very quickly and easily figure out at what values of x, if any, the polynomial or the quadratic expression is going to be 0. Okay, so anyhow, zeros of the numerator are at negative 2 and negative 3, and the denominator has a 0 at 3. It's very obvious that x minus 3 is going to be 0 if and only if x is 3. Okay, so we can draw an x-axis and we can mark our critical points. Now the rest of this wasn't originally marked. We would just draw the x-axis. We mark the points negative 3, negative 2, and 3 on the x-axis. It's not necessary to draw the y-axis, but if you wish, it would be between negative 2 and 3, a little bit closer to negative 2, probably about right here. I didn't draw it because it's unnecessary. Okay, but if you're trying to graph the function, you do want to draw the y-axis and figure out the y-intercept. It's a point that's very easy to find. It's worth doing. If all you're trying to do is get an idea of overall what the function looks like, it's often optional whether you draw the y-axis. Never a bad idea to do that, though. Okay, now, the points negative 3, negative 2, and 3 partition the x-axis into intervals. The interval to the left of negative 3, the interval from negative 3 to negative 2, the interval from negative 2 to 3, and the interval from 3 to infinity. So between these points, we have these intervals. When I said we partition the x-axis into intervals, actually, a partition has to include all the points, so these would have to be half-closed intervals. But we're not going to worry about that. Okay. Now, all you need to do to determine whether the function is positive or negative on any given interval is plug in the coordinates of any point in that interval. Not at negative 3 or negative 2 or 3, because you're going to get a 0 of the numerator or a 0 of the denominator, and you're not going to get a lot of information. But points in these open intervals between the points. Okay, so to the left of negative 3, there are two ways to reason this out. One way, somebody said, okay, let's use x equals negative 4. Perfectly valid. Okay, so we did that. We let x equal negative 4. F of x is this. If x is negative 4, f of x is this. And you can certainly follow this. I don't have to read it to you. And this is negative because negative 4 plus 2 is negative. Negative 4 plus 3 is negative. and negative 4 minus 3 is negative. So we have a negative times a negative times a negative. Well, negative times a negative divided by a negative, but that's going to give you a negative. Okay? A negative times a negative is positive, and if you multiply or divide a positive by a negative, you get a negative. So, we conclude that f of x is negative on this interval. So, I can say, okay, from here over, then I know that the graph is going to be, or that the value of the function is going to be negative, because the only place the graph can change sign is at one of the critical points. It can only become positive by going through the x-axis. So, negative over here. Now there's another way it could become positive, but in this case, negative 3 is 0 the numerator, and so is negative 2. So the only way it can change sign at negative 3 or negative 2 is to go through the axis. Okay, well, then between negative 3 and negative 2, okay, we use negative 2.5. Now we don't have to do all the arithmetic. All we have to know is whether each factor is positive or negative. So we put negative 2.5 into this expression, and you can verify this is what we get. Negative 2.5 plus 2 is negative. Negative 2.5 plus 3 is positive. 3 is bigger than 2.5. Negative 2.5 minus 3 is negative. So we have negative times positive, which is negative, divided by negative. That makes it positive because we're dividing a negative by a negative. So the graph is positive, the function is positive between negative 3 and negative 2. Then between negative 2 and 3. Okay, well, let's see. The easiest number we can use between negative 2 and 3 is 0. If we let x equal 0, and I'm looking for it here on the board, I don't think I even wrote it out. Here it is. If x equals 0, f of x is what? Well, 0 plus 2 is 2, 0 plus 3 is 3, and 0 minus 3 is negative 3. So we can actually calculate that. And as I said, sometimes you want to draw the y-axis and put the y-intercept on the graph. So we could multiply this out, we get negative 2, and that is the y-intercept. For the purposes of just determining whether the function is positive or negative between negative 2 and 3, we find that it's negative because it's negative at 0, which is between negative 2 and 3, and it can't change sign between negative 2 and 3 because there are no critical points between negative 2 and 3. So the function is negative on this interval. And then we can easily determine that the function is positive on the interval from 3 to infinity. Okay, somebody wanted to use x equals 4, so we used x equals 4, and we found that every one of these numbers turns out to be positive, so we have a positive times a positive divided by a positive, which is positive, so now we know that this function is positive from here on. Now there's another way where you don't even have to use numbers to determine, for example, that x is negative to the left of negative 3. There's some really big negative numbers to the left of negative 3. If you put a really big negative number in for x, well, x is positive in every one of these factors, so that really big negative number is going to make each of these factors negative, isn't it? Okay? Because x is a really big negative number. It's a lot bigger than 2 or 3 or negative 3. So no matter what numbers you have here, x is big enough that it makes every factor negative. So you still have negative times negative over negative. Still have negative. And you don't have to even put numbers in. Similarly, on 3 to infinity, you know that there are some really huge positive numbers. Okay, so you just reason out, if x is a really big positive number, well, this has a positive x, this has a positive x, and this has a positive x. So this is going to be a big positive number, this is going to be a big positive number, and this is going to be a big positive number. If x is a really big positive number, subtracting 3 from it doesn't change the fact that x is still a really big positive number. So you're going to have positive times positive over positive. It's going to be positive, and there you have it. Okay, so this is how we determine where the function is positive and where it's negative. Now, I haven't talked about the graph and how I got the shape of this graph. That's not actually part of the problem, but we do want to address that. So I'm going to talk about that in another video, especially about how the function acts near the zero of the denominator, because you will need to be able to graph functions of this nature.